Welcome back to this course on Computer Architecture Fundamentals. In this lesson I will show how loop unrolling can be applied to further improve the performance of our code example. Loop unrolling, also known as loop unwinding, is a relatively simple but very powerful and effective technique to reduce loop overhead. It replicates the body of the loop multiple times. The number of replications is sometimes called the loop unrolling factor. In order to do so, the loop termination code as well as some address calculations, however, need to be adjusted. I will illustrate loop unrolling using our example loop that adds a scalar to all elements of an array. If we unroll the loop 4 times, the unrolled loop will look like this. The loop counter I is now incremented by 4 instead of by 1, and each iteration now calculates xi, xi plus 1, xi plus 2 and xi plus 3. Notice that this transformation is allowed because the number of iterations, the loop count, is 1000, and this is a multiple of the loop unrolling factor of 4. But in the general case, this need not be the case, because the loop count n may be unknown at compile time, or n may not be a multiple of the loop unrolling factor, say k. In such cases we require 2 loops, one that is unrolled and iterates n diff k times. In this expression, diff denotes integer division, so for example 7 diff 3 equals 2. And we require another loop that is a copy of the original loop and that iterates n mod k times. The modulo or mod operation yields the remainder of interdivision. So for example 7 modulo 3 equals 1. Unfortunately, integer division and modulo operations are very expensive, long latency operations that should be avoided if possible. Luckily, usually they can be avoided using a trick. To illustrate this trick, let's consider again our example loop, but now the loop bound has been replaced by a program variable n, as highlighted by the red font. The first loop is unrolled by a factor of k. So the loop counter I is incremented by k in every iteration, and each iteration calculates the elements xi, xi plus 1 to xi plus k minus 1. The loop test is now replaced by the Boolean expression I plus k minus 1 must be less than n. Since I plus k minus 1 is the last element computed in iteration with index I, this assures that the array index is within bounds. The second loop is a copy of the original and performs the remaining iterations. The loop index I is not reinitialized at the beginning of the for loop, but still has the value it had after completing the previous loop, as indicated explicitly by the empty statement in the form of a comment in the initialization part of the for loop. Let us now look at how the example assembly loop will be unrolled and executed. This is again our example assembly loop, and this is how the loop looks like if it is unrolled by a factor of 4. 4 times we load an element of x, add the scalar to it, and then store back the new value to memory. The only difference between each instance of load double and store double is the offset. It is 0 for xi, 8 for xi plus 1, 16 for xi plus 2, and so on. But does this loop really run faster than our previously scheduled loop? Unfortunately not, because when this code is executed there will be many stall cycles as shown here. Because every store double depends on the preceding add double, which in turn depends on the previous load double, there will be 3 stall cycles per element xi. In fact, this loop requires 28 clock cycles, 14 instructions plus 13 stalls plus an empty branch delay slot. In other words, 7 clock cycles per element are required, which is slower than the previous scheduled loop, which took 6 clock cycles per element. Question: can we reschedule the instructions in order to eliminate some or all of these stall cycles? For example, the second load, highlighted here in green, is not dependent on any of the preceding instructions. So can it be moved immediately after the first load? Unfortunately, not like this, because the second load uses the same destination register or name as the first load. If it would be moved after the second load, the first add double would use the wrong value. To be able to reorder the instructions, we need to use different or rename the registers. To illustrate this, here's again our example unrolled loop. And here's the loop after the registers have been renamed. Instead of reusing F0 and F4, the computation of the second element xi plus 1 now uses the registers F6 and F8 as indicated by the red color. Similar, the computation of xi plus 2 now uses the registers F10 and F12 as indicated by the green color, and the instructions that calculate xi plus 3 also use different registers as indicated by the blue color. After renaming the registers, we are able to reorder to schedule the instruction to improve the instruction schedule. Now I show how the code should be scheduled to eliminate all stalls. Here's again the unrolled loop after register renaming, and here's how the loop should be scheduled to avoid all stalls. First, at the top, we execute all loads. This is possible because all loads write to a different register thanks to register renaming. Then we execute all add doubles. Because there are now 3 instructions corresponding to cycles between the load of a value and its use by the corresponding add double, the stalls due to the load use data hazards have been eliminated. In fact, 1 cycle between the load and its use would have been sufficient, so 3 is more than enough. Then we schedule the first 2 stores. Also here, there are 3 cycles between an add double and the corresponding store, which is more than sufficient to hide the 2-cycle latency. Then we execute the add immediate and we schedule the 3rd store between the add immediate and the branch in order to eliminate the stall cycle that otherwise would have occurred between the add immediate and the branch. Again, we have to adjust the offset of the store because now it occurs after the add immediate. And finally, we move the 4th store in the branch delay slot, also with an adjusted offset at the bottom. So we see that loop unrolling combined with register renaming enabled us to schedule the loop without stalls. An interesting question is, can the loop be scheduled without stalls if the loop unrolling factor is less than 4? If it is unrolled 2 or 3 times? I leave this as an exercise for you. Here I show again the final unrolled and scheduled loop. It requires 14 clock cycles per iteration and incurs no stalls. In other words, 14 divided by 4 equals 3.5 clock cycles per element are required, since every loop iteration calculates 4 elements. This is quite close to the minimum of 3 cycles, since at least 3 instructions are required per element: the load of the element, the add double, and the store of the result. This has been made possible by first moving all loads before all floating point additions and all floating point additions before all stores. Second, by moving 1 store between the add immediate and the branch. Third, by moving 1 store in the branch delay slot. And finally, by using different registers for the calculation of every array element. We were able to do so manually by using our programming knowledge and our knowledge of the pipeline organization. But of course, instruction scheduling is in most cases not done manually, but by the compiler. So the question is, when is it safe for the compiler to perform these changes? This slide summarizes the steps that the compiler must perform to reschedule the loop. I will not read from the slide, you can read it for yourself. To make it easier for you to read, I switch to full screen mode now. Finally, a few words about the advantages, the pros, and the disadvantages, the cons of loop unrolling. The advantages of loop unrolling are: first, it reduces loop overhead. Loop overhead is now incurred once per loop iteration, so reducing the number of iterations as unrolling does reduces the overhead. The second advantage is that it improves the possibilities for instruction scheduling. Instead of having to find independent instructions that can be rescheduled in a single loop iteration, loop unrolling allows finding independent instructions across several loop iterations. In a later lesson, I will discuss dynamic and speculative techniques that basically unroll loops during program execution. Disadvantages of loop unrolling are also present. First, it increases the code size. Increasing the code size and therefore increasing the size of the memory needed to hold the program code can be a major concern in the embedded domain, in particular in domains where profits are minimal and therefore every penny counts. It can also be a concern in desktop and server computing domains because larger code size may increase the instruction cache miss rate. Therefore, loop unrolling should not be overdone. Another potential disadvantage of loop unrolling is that we, or the compiler, may run out of registers to keep all intermediate results. The number or percentage of registers needed to keep all intermediate results is sometimes termed register pressure. It's another reason why loop unrolling should not be overdone. This completes this lesson. Thanks for watching. In the next lesson, I will give a summary of this module in which we extended the canonical pipeline with multi-cycle operations. Hope to see you back.